All right, welcome everyone. It is May 2nd or 3rd? It's May 2nd. Okay, I want to thank Tariq and SITTV for being here tonight. Thanks to them, we have this recording. I want to welcome you all who are here, the home audience and the studio audience. So tonight, our goal is to go through an E232 final. And if I can just walk over here, the final we're going to do is from the spring of 2014. This final is posted on the course website along with the solutions. Now, my colleagues, what does the final cover? The final covers from the very first lecture to the very last lecture. So our last lecture is this week. So the material that we're going to cover this upcoming Friday is also on the final. So this exam may not reflect that because we're going to be discussing, I think, some new material that's not in the book. So I would encourage you all to come to class on Friday, but you're here, so you would be at class anyway. So we have class this Friday, and the final will cover through that last lecture. All right, I'm excited to get going. I welcome your questions. So let's get started. Spring 2014, final exam. Oh, by the way, a question I typically get is what's the formula sheet? I might update the formula sheet because it's gotten a little messy, but basically the formula sheet for now anyway is what's posted on the course website, okay? So we look here and say, great, let's start out with, Let me not look at the answer yet. Problem 1, so I say, okay, that's a good place to start. Problem 1, and we say, what do we have here? Oh, this reminds me a little bit of exam 1, but I'm wondering if it was extended to include other topics. So let's see if we can figure this out. You're given a sensor, which can be modeled as a first-order system. I'm hoping this is like gold stuff for you now. So we have a first-order system sensor, which can be modeled by a first-order differential equation. The input is a constant. The input has a value of 55 for all t greater than 0. The initial reading of the sensor is minus 12.7. Time constant for the sensor is 4.6. So I think I give you all the information. All right. So part A, determine the output 11.3 seconds after the input has been applied. So Ronnie, what I'm thinking is I go back to the concept of first order, and I say that first equation up there. So my colleagues, just so I'm wondering, did I? Yeah, I think I wrote this backwards by accident. I'm sorry about that. I mean, it's correct, my colleagues, but I just switched the x and the y. Normally, the input is x, okay? Here, I said the input is y. So sorry, my bad. The output is normally y of t, and in this solutions, I made it x of t. So sorry about that, but we still get the right answer. I just switched the x's and the y's, all right? Now, I know, and I know that you know, the solution to the first order system is ke to the minus t over tau. That's the homogeneous solution, plus the particular. And I know you know, that for a first order system with a constant input, the particular solution is the right-hand side. Okay? So that constant is 55 because that's the input. Okay, so what we have is the particular solution for a constant input in a first-order system. The particular solution is the constant input, what we call the right-hand side. How do I determine K? Initial conditions. I'm given that. The initial condition is minus 12.7 at t equals 0. I should get K to be minus 67.7. So my colleagues, the real first part of this problem is to get this equation, which I get from the constant input. I get this value here from the initial condition, and the form is the general form for the solution of a first order system. Now let me pause. Are we all here? Is everyone solid how to get down this far? All right, so I say good. Now, we were asked to figure out the value right, look what I did. My colleagues, what was I doing as I was writing this? My colleagues, I now switched. This is going to drive everyone crazy. I did this unintentionally. I'm very sorry. I started out by saying, okay, I made a mistake. Y is the input, X is the output. And I guess, Eamon, unconsciously, I said, no, once I do all of this, Y of t is this. Y of t is this. And I say the initial condition, Y of t is this. So now I'm okay. So my colleagues, I apologize. Home audience, I'm very sorry. I now switch and I make Y the output and X the input. Okay? But either way, I think we get down here that the output is minus 67.7 times the exponential plus 55. I'm sorry for the confusion. It was a mistake on my part. I didn't mean to do it. But I think we get to the right point. How are we all doing? Okay. So I say, okay, all of this is good. And now it's just plugging it in. We like to know the reading of the sensor at 11.3 seconds. So I put in the value of t to be 11.3. And I get the total answer. I put the time constant in. The time constant was given to be 4.6 seconds. Plug it all in. 49.2 is the value of y at 11.3 seconds. Part A, done. Are we all good? All right. So I say good. This is good. Now, what does part B? I'll raise it in just a moment. Determine the time it will take the sensor to reach 90% of the final value. What's the final value? Right, the input. Exactly. Excellent, Chris. The final value is the input because it's a constant input. So now we have to figure out how long it takes to get to 90% of the final value. So I say, okay, I think I can do this. Final value is 55. 0.9 of 55 is 49.5. And then I go back to the equation that I had in part A, and I now put that the output is 49.5. That's 90% of the final value. And I know everything. Tau was given, same tau, except t. So I step you through this. We subtract, we divide, we take the natural log. Ronnie, my colleague, are you concerned that at this point of the problem, I'm going to get t to be minus tau times this natural log? Am I getting negative time? Why? Why not, Ronnie? Exactly, Ronnie. We're taking the log of a number less than 1. So this itself is negative. So we have a happy ending. Everything turns out fine. Okay. So I get t to be 11.5 seconds. I plug this in just to double check it. It checked. So there you have it. That is the value of t for 90%, to get to 90% of the final value. How are we doing? Kevin, we're good? Eamon's good? All right, we're good? We're good. All right. All right. All right. Oh, we have more. I give you the answer here. All right. It says, we now have a ramp input. Oh, for those of you who were at our exciting lecture last week, this is like, okay, I got this. We now have a ramp input to a first order system. What is the time delay? Okay. Will, this is what I remember. Time, and let's call this the output. Now, this should be the ideal output. And my colleagues, I hope you remember, we get an exponential rise, and then we're in steady state, we're parallel. And as I hope you remember, and I'm sure you do, the delay is saying, at this point right here, let's call it T1, I am reading a certain value, but I am off. So how long is it going to take me until I record the value I should be recording now? That's the delay, and that is tau. Now, you can prove that yourself by going through the equation we had in the notes, or, Wesley, what can we do? Just remember it. Just remember it, okay? So you don't have to prove it. The delay for a first order system to a ramp function is tau. Now, come on, you know me well enough, all the tests we've had. What's the next question I ask you? Pardon? The answer is, it's like Jeopardy. You give me the, this is great. You give me the answer. The answer is a tau. What's the question? What's the instantaneous error? Okay? Ronnie, that's what I should do. Wouldn't that drive everyone crazy? I just wrote down problem 1, part B, a tau. Just see what, that's the instantaneous error. Okay. Oh, that'd be, boy, a Jeopardy exam. Oh. First order systems for 500. There it is. Instantaneous error is a tau. Now, Ronnie, the instantaneous error, I think, is the vertical difference, the distance up and down. Okay, so what the value should be right now, that's the instantaneous error. Okay, good. We're doing good? Now, I don't know what's coming next. I don't know if I have another one. I think we switched to maybe a different problem now. Yes, we're on to problem 2. That's problem 1. Before we shift gears and go on to problem 2, are we all okay? Okay, good. Caroline? All right, she gave me thumbs up. Good, good. All right, so we're all set. We're doing good. Now, just from the layout of the problem, what does this bring back to mind? Chapter 5, Chapter 2, Chapter 6, Chapter 9, Chapter 10? I think it's Chapter 7. I think. Because okay, we're given a measurement system. Okay, remotely measure air quality. Great. The remote sensor is connected to a wireless network for transmission to a central control station. All right, so we have a sensor. So I kind of changed the order a little bit. We have a sensor going into a wireless network. Let's call it a wireless LAN. And the received signal is then filtered at the control station. So it's filtered. We go through a filter, probably to get rid of noise. Amplified. Oh, great. And I guess the filter is also acting as an anti-aliasing filter. Amplified. And then we go through an A to D converter. Can I call that an ADC, just to save all the writing? There you have it. Okay? So, my colleagues, what we now got to do is just keep track. Keep track of the randomness. And we're going to add it all up. Okay? So, I'm going to say, all right, good. So, I'm looking here. Now it's just a matter of reading the problem. Now, my handwritten notes are not given on the exam. So you have to know that whatever sensitivity, linearity, and hysteresis is, they are systematic errors. So you got to know that, but since you're here, or since you're watching it, you know it. So these become systematic errors. So tell you what, that would be the sensor. This is a systematic error. So this is a bias, a B. All right. Now, the range is plus or minus 3,000, full scale. I think you know this because I asked this during the lecture. What's full scale, 3,000 or 6,000? 3,000. Good man. Full scale is 3,000. So as I'll show you in a moment, it's all calculated down here. I'm going to calculate 3 items. First one, 0.25 over 100, because it's a percent, times 3,000. And I do the same for the 0.15 and the 0.10. So let me just jump down and show you that. I guess I do this all on the next page. You know what it is? I asked for the systematic error in Part B. So let me, with your permission, let me do Part B first. Okay? So now we get calculation of the sensitivity, the linearity, and the hysteresis. And just to follow what we did in the lecture, this becomes 7.5, 4.5, and 3. And Part B says determine the total systematic uncertainty. Now, my colleagues, if we read the rest of the problem, there's no other systematic error. Okay, so we'll go back and do that. But if we read the rest of the problem, there's no other source of systematic error. So the sensor is the only source of systematic error. And you know this. How do we add in Chapter 7? RSS. We square, sum, square root. So RSS backwards. Square, sum, take the square root. So we add the systematic error using RSS. 7.5, the 4.5, and the 3. Again, RSS, we square. Sum, take the square root. This is now the systematic error. That's the answer to Part B. Part A says determine the random uncertainty. Okay, that's what's coming. I should have maybe done that first, but it's okay to do things out of order. Now we'll go back and do Part A. How are we doing? Good? All right, good, 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 good. Now we go back to Part A. And I said, okay, I've kind of started this process. Let me see if I can continue it. Now, it says to determine the repeatability of the measurements, a large number of auxiliary tests were done on the sensor. And the standard deviation of these measurements is 4.3. So I'm going to start another column. S for standard deviation, 4.3. Now, my colleagues, I think this came up in both lectures, in both sections. This issue here of getting 4.3, Eamon, most likely that was done by the manufacturer of the sensor. They are the ones who made all these auxiliary tests. And they determined the randomness that was left inside the sensor after they had designed everything. So we got a standard deviation of 4.3. Okay, so I just continue on. The wireless network. Again, a large number of tests. Who did that? Probably the provider of the wireless network. Has a standard deviation of 1.7. So I'm going to start the S column for the wireless LAN, and that's 1.7. All right. Separate test of the filter, standard deviation of 1.3. So I run over here. Standard deviation of the filter is 1.3. So far, I think we're doing pretty good. I think. Now, the author, because I worked with the author's problem here, the author tries to fool us. A to D converter has the random uncertainty of 2.5. Random uncertainty of 2.5. Now, the random uncertainty of, did I forget the amplifier? I'm sorry? Oh, it's down on the bottom. Thank you. Let me do it since, okay, we got 1.5 for the amplifier. Thank you. Now I'm up to the A to D converter, a random uncertainty of plus or minus 2.5. Okay? Now, what I remember is random uncertainty. I vaguely remember chapter 6 and the student t distribution. And we had plus and minus. I think it was t alpha over 2 times the standard deviation. Then we had over the square root of n, but we have n equal 1. We're taking a single measurement here. So it becomes times the standard deviation. Now, that's what I want. I want S because everything else is S. Right? So I say, okay, how do I get S? Well, I'm given the random uncertainty. So I'm given this. So the random uncertainty is 2.5. What do I do to get S? If I know 2.5, Amen, you're smiling, I love it. What do we do? I think we had T for 2 and 2 for T, right? You have no idea what I'm saying. That's okay. It's an old, old song. Okay, so 2. That was our symbol, I think, in the afternoon class. So, Amen, there's probably someone out there, maybe Ileana, who sits up here in the class. She's probably not happy now because she knows it's not exactly 2. Amen, what is it exactly? Do you happen to know? 1.96. But the book, and many people say that's close enough, especially after 14 weeks together, we'll call 1.96 2. Okay, so now we got 2. So 2.5 equals 2 times S. All right, so what do I get? 2.5 divided by 2 is what, 1.25? All right, so S here equals 1.25. Okay. Now, questions I got during class, it's 2 or 1.96 because of 95% confidence. Are we always going to have 95% on the exam? Is yes. So my colleagues, the bottom line is always going to be 2 times S equals the random uncertainty. All right? Now, I think we've done all the hard work. It's now just an RSS. So I think I have all the numbers, right? Standard deviation of the sensor, 4.3. Wireless LAN, 1.7. The filter, 1.3. The amplifier, 1.5. And this becomes 1.25. Now, what do we do to get the total random uncertainty? Well, the first thing we do is, now that everything is in standard deviation, we take all the S's that we have on the board here, and we now add them up using RSS. So we square, sum, take the square root. So I got a standard deviation of 5.185. Is that the answer? No. Exactly. Why not? What do I now have to do, and why? We're asking for random uncertainty. I think I have to multiply by 2, because random uncertainty is plus or minus t, alpha sub 2, times S. So I now have to multiply by 2. I give you a little description of why we're doing that. We get this, and now we're done. I think I have a part C in which I ask for the total uncertainty. How do we do on parts A and B? All right. My colleagues, I think we're doing good. I think we are. Part B we already did. And then part C talks about the total uncertainty. Total uncertainty is the systematic uncertainty plus the random uncertainty, except all we do is an RSS. So take the answer from part A, the answer from part B, and do an RSS. Square, sum, square root. And we got it. That's it. 2 problems done. All right. Anything I can help with, my colleagues? All right. I still see some people writing. I'll give you another moment. It'll give me time to take a quick drink of water. All right. Oh, no. One of these sensors. One of these sensor problems where everything is independent. I bet you there's a graph here or a drawing or something we have to look at. So refer to figure 1 at the end of the exam. I give you all, I don't know what I was thinking. Why couldn't I have just said the probability of all is 0.8? I don't know why. I wrote it out, Ronnie, I don't know what the heck I was doing. I don't know. So determine the probability the system of sensors is working properly. Are you all okay on this? How do you solve it? What's the trick? Come on, here. I even forget what the figure is. But my colleague Max, in the 3 o'clock class, Max, I bet you I got sensor 1 and sensor 2. Now, my colleagues, I claim if you can do this, there's nothing I can throw at you you can't do. How do I determine the probability that that's working? Sorry? Right, exactly. So the only way this doesn't work is if both are bad, which if the probability of a sensor working is P, the probability of a sensor not working is 1 minus P. So if I have n sensors in parallel, the probability of it not working is 1 minus P to the n. So what's the probability of it working? So the only way this parallel combination of sensors do not work is if both sensors don't work. So that's the probability of not working. Probability of working is 1 minus that. If you got that, I don't think I can trick you. So let's go to figure 1. Can you get this? I bet you can. Hey. What do you think? You think we can do this? All right. I hope I don't make a mistake because this is being recorded. It will go up on YouTube. Will be there forever. My grandkids will be seeing me make a mistake. So I need your help to make sure I don't make a mistake. All right? So what's the probability of the bottom path not working? Probability of the bottom path not working is 1 minus P squared. Do I have that right? Probability of the bottom path not working is 1 minus P squared. Okay? Now, the probability of, how about sensors 1 and 2? What's the probability of sensor 1 and sensor 2 working? What's the probability of sensor 1 and 2 working? Sorry? No. Exactly, Wesley. Perfect. Wesley, that's 1 minus P squared. Wesley, did I get it right? That's the probability of getting through. I didn't say this very clearly. This is my bad. It's not sensor 1 and sensor 2 working. That's not a clear way to say it. It's getting through sensors 1 and 2. All right? How do I do that? Here, I don't know if this makes sense. Help me out. Getting through the parallel combination of sensor 1 and 2. 1 and 2. Does that make sense? I asked the wrong question. You gave me the answer to what I asked. What's the probability of sensor 1 and 2 working? It's p squared. But as you know, Wesley, because then you corrected me and you were right, I can get through that if sensor 1 works and sensor 2 doesn't. I can get through there if sensor 2 works and sensor 1 doesn't. So the probability of getting through 1 and 2 is 1 minus p squared. We're good? Now, the probability of getting through 3 and 4, Ronnie, that should be the same. So that's 1 minus p squared. Right. Now, I now figure, what's the next probability I have to figure out? Sorry? Right. The probability the whole top works. The probability that the whole top path works. What's the probability of the whole top path working? It only works if I get through 1 and 2 and 3 and 4. And since this is all independent, what I get is 1 minus p squared times, let me write it out the long way, times 1 minus p squared. That's the probability of the top path working. How am I doing? What's the next probability I figure out? Chris? Yeah, we got the bottom. Good. I think, Chris, what I like about the bottom is that's the probability of the bottom path not working. I need to know the probability of the top path not working. So what I do is I know the probability of the top path works. So now, what's the probability of the top path not working? That equals 1 minus p squared, all of this squared. Ronnie, am I doing okay? Now, I now know the probability of the bottom path not working, the probability of the top path not working. This is just like two sensors in parallel. Right? So now I say, okay, when does this whole system not work? When the bottom path and the top path don't work. So I know the probability. Can I erase the middle here? Am I doing okay? For those of you at home, you're saying, what is he doing? I don't know. It's all written down, but I'm having fun just seeing if we can do it on the fly like this. Okay? And if I'm wrong, I don't know. We'll have to start the whole session over again. I don't know, Will. This is it. All right? But this is what happens with live TV, Will. You know? All right. Now, Will, I don't want to lose my focus. All right. So I now know the probability. Bottom path does not work. Top path does not work. So therefore, the probability that the system does not work is this times this. Because the only way the system does not work is if the bottom path doesn't work and the top path doesn't work. So this is 1 minus p squared times 1 minus, a lot of 1 minuses here, 1 minus 1 minus p squared I don't want to lose a square here. What's the last step? Probability the system works. Now, my colleagues, I have to calculate this. It's 1 minus p squared. 1 minus 1 minus p squared, boom. Is that everything? Does anyone have, Ronnie, can you help me out? You got a good calculator to do this? Good man. P is 0.8 for the whole board. You already did it. So what did you get? So you got 0.997. Now, we need a drum roll. I'm nervous, Eamon. No, I'm the one nervous. Counterclockwise. Is 0.9968 close enough? So that should be it. We did it. All of us did it. You were looking over my shoulder. We did it. Okay? So my colleagues at home, if you were like, well, what's he doing? That's okay. I did it here using numbers. My wording was nicer here. Look at that. That was very nice. The probability of at least one path working through S1 and S2. That's what I should have asked you, Wesley. And we got that to be 0.96. Then the probability of at least one path working through S3 and S4. The probability of the upper path working. The probability of the lower path working. Probably the upper and lower path not working is then here. And then finally, we do, I think, 1 minus that to get the probability of at least one working path through the network of sensors. And Ronnie, thank you. So it looks like we're accurate to 3 decimal places, so I think we did it right. All right, we're good? All right, excellent. That's the third problem. We're moving on here. A binomial distribution problem. Boy, I wasn't expecting this on the final, but we got it. So we have a binomial distribution problem. I'll give you a moment to read it, and we'll figure it out together. All right. Sound quality is still good? Great, thanks. All right, so you have a packet, which is a group of binary digits. I don't necessarily need to know that. But I'm watching a video, and what's happening on my tablet device is I'm receiving groups of bits so I can view the video. And this group of bits is called a packet. Perfect. Okay, fine, great. Now, the probability of a video packet being received in error is 0.15. So the probability of getting a packet in error, 0.15. Now, this is interesting. 10 video packets arrive at your tablet device or your smartphone. Now, your smartphone and tablet device have a way to correct errors, but only up to a certain number. If there's too many errors, it's hopeless. If there's a few errors, we have a chance we can correct them. So the receiver can correct up to 2. That means it can correct up to 2 video packets in error out of the total of 10. Determine the probability there's no more than 1 video packet, no more than 1, received in error after the error correction process. This sounds confusing. This sounds, I mean, I think the guy who wrote this, I think he was out to just confuse everyone. All right? So you get 10 packets. And what it's saying here, if 2 are in error, we can correct up to 2 of them. So I kind of wrote all this down just so I could understand it. Probability of a packet in error is 0.15. But the big but is up to. 2 packets can be received in error and be corrected. So that means 0 or 1 or 2 packets received out of the 10 that may be in error results in 0 packets. Because I'm correcting 0 packets in error, because I'm correcting 2. My colleagues, help me out if I'm not making sense. So that means, reading again, so the probability of no more than 1 packet in error, no more than 1 means 1, and 0. Now, how do I get 0 packet errors? If I received 0 packets in error, or if I received 1 out of the 10 in error, or if I received 2 out of the 10 in error. Those 3 events count as 0 packet errors. And I want to know the probability of no more than 1 packet in error. Well, 1 packet in error would then be receiving a packet, 3 errors. 0, 1, 2. This is the hardest part of the problem. The rest is just plugging in. Am I doing okay? If you have a doubt, you got to tell me, because someone out there is like throwing stuff at the screen. They don't know what I'm talking about. Someone's got to help me out. Do we have a question? See, if I get 2 packets, if I receive 2 packets and 2 packets are in error, I can fix them. So the end result is 0 errors. If I have 3 packets arrive in error, I can fix 2. I still got 1 I can't fix. So, for me to get 1 packet in error after doing this correcting, I really had to get 3 packets in error. And to get no more than 1 packet in, no more than 1 means 0 or 1. That means I could have received 0 packets in error, or 1 packet in error, or 2 packet in error. That all results in 0 errors. The 3rd packet in error is too much, I can't correct. So 3 packets in error results in 1 unfixable error. Let me pause. Am I doing okay? Because I'm concerned about the home audience also. Am I doing okay on this? Did I describe it okay? All right. Thank you. Thank you. My pens are dropping all over the place here. So I say, good. Once I got through that, the rest is I think, just plugging in. Okay? So, okay, let me just say it again. What I have to calculate is the probability of 0 packets in error, 1 in error, 2 in error, 3 in error. That's the key. Once you got that, I think we got this. Now, remember how the binomial distribution works. So I want 10, choose 0. 0 packets in error. Okay? Now, as pointed out, the probability of an error is 0.15. In 10, choose 0, how many error packets do I want? 0. That means the probability of not getting an error is 1 minus that. That's 0.85. And if 0 packets are in error, 10 must be no errors. Sorry? We're okay? Good. Sorry, Ronnie. And we do that again. Let me just write down one more term. Probability of 1 packet in error being received before we correct is 10, choose 1. 1 packet in error is 0.15 to the 1, 0.85 to the 9, and so on. It's all written up here, and you get 0.95. I think, Ronnie, that's what you were doing. You were giving me the thumbs up. You had already calculated it. So the probability of no more than 1 video packet in error is 0.95. That's our binomial problem. How did we do?
The binomial equation is on the formula sheet, right?
I'm almost positive it is. The binomial, I know it was on exam 2. And I think I pretty much kind of just joined exam 1 and exam 2, and then I add extra stuff for the other material. So I'm almost positive it's there. Good. All right. All right, I think that's what, problem 3 or 4? Problem 4? We're up to problem 5. So far, so good on the first 4? All right, problem 5. This looks like parameter estimation, okay? Like we had on exam 2, parameter estimation. All right, now, you measure the following sensors and you get these readings. It's measuring power, it's in milliwatts. I measure 4 sensors, you know this. What's important about 4? Less than 30. So it's student T, okay? So right away, you know it's student T. Determine a 90% confidence interval on the mean. So a 90% confidence interval on the mean. Wesley, I'm pretty sure I also give you the standard deviation formula for the sample because it's n-1 in the denominator. So my colleagues, what we do here is we find the average of the 4 and we find the standard deviation of the 4. Okay? So the standard deviation, you probably recall, is the average minus the value or the value minus the average, it doesn't matter, squared. So you do that for each of the 4 terms. You then divide by n-1 because it's the standard deviation of the sample, and that's on the formula sheet. So you divide by 3, and it's kind of falling off the screen there. That's meant to be raised to the 1/2, so I'm taking the square root. And I have that down here, and I get the standard deviation. So now I say, good. I think we're good. I like these problems. I think they're kind of fun. They're easy, and they really give you a lot of insight. Now, this formula should also be on the formula sheet. So the whole thing with parameter estimation is mu is the average of the population, which I don't know, because the population would require me to measure everybody or everything. I don't know that. So I measure a handful. Okay? So notice with the square root of n in the denominator, the more I measure, the plus and minus become smaller. The less I measure, the plus and minus is bigger, which makes perfect sense. The less I sample, the more uncertain I am. So we get x bar plus and minus t, because it's 4, not less than, it's 4 less than 30, and s over the square root of n. Now, my colleagues, please make sure you're comfortable in reading both the z table, which is coming up in another problem, and the student t table. So if I'm 90% confident, alpha, my colleagues, that's the area under the tails. So if I'm 90% confident, I'm 10%, 0.1, not confident. So the table is organized by alpha over 2. So alpha over 2 is 0.05. Now what do? I go down the rows on the table. Be careful, don't make a mistake. I have to use degrees of freedom, which is n-1. So we had 4 samples. Degrees of freedom is 3. So go down to the row with 3. Read across till you get to alpha over 2 is 0.05. And we get a value of t alpha over 2 to be 2.353. At this point, you're done. Okay, it's now just plugging it in. And you can write it either way. So I'll probably write it both ways on the answer key. Either way you want to write it. So mu is x bar plus and minus. How did I get to 2.02? That's t sub alpha over 2 times s over the square root of n. I get this, or you can write it this. We're done. That's a student t basic parameter estimation. I love it. We're done. We're good. All right. Good. Okay. Okay, we're up to problem 6. All right. Okay, I'll give you a moment, give myself a 10-second break here. Okay, you're given a function that has 4 frequencies. The first one is 5 sine of 375 pi t, and then it goes on. So there's 1, 2, 3, 4 terms. All right. Now, just to make sure you don't make a mistake, I mean, this is very basic. I know you know it, but sometimes we forget the most basic things. The standard way of writing a sine or a cosine inside the argument is 2 pi ft, or omega t, where omega is 2 pi f. So if I write it as sine of 375 pi t, that means 375 pi t equals 2 pi ft. So notice the frequency is not 375, it's half because of that 2. Just be careful, that would change the whole problem. Okay? So now we get the 4 frequencies. So the 2 highest frequency terms are unwanted noise. This function is to be converted to a digital signal using an A to D converter. Now, we apply this signal without an anti-aliasing filter. Not that you would ever do this, but suppose you did or someone else did. So now you put this term f of t into an A to D converter without first using an anti-aliasing filter. I know the answer is here, but I'm hoping you would have gotten it anyway. What's the minimum sampling rate of the A to D converter? Chris? That's it. That's it. Yeah. If I could add to that, Chris, it's twice the highest frequency. Perfect.
Depends if you want the cutoff to be, if you had a value of 3,000, you said I want it to cut off after
Right.
1375.
Exactly. So, Chris, that's the point I get to in the next part of the problem. That's excellent. So what we say here, my colleagues, is there is no anti-aliasing filter, and as Chris is pointing out, we don't yet have the concept of a cutoff. We have nothing. We're just putting the whole thing into the A to D converter. Go to the highest frequency, which is the 4th term, 1375, double that, 2750, and we're done, part A. All right. Now, part B says, all right, now we're going to do the anti-aliasing filter. And I ask, what's the cutoff, or sometimes called, as Chris used the term cutoff, which is perfect. We also can use the word corner frequency. So what we've done in class is to say, wait a minute, there's 4 terms here. I think it said in the problem, the top 2 terms were not needed. Okay? So we go back and say, all right, I want to get rid of the top 2 terms. Now, in our course, what we've been doing up till now is we have made the corner or cutoff frequency equal to the highest frequency you want to get through. So you would say the cutoff is 637.5. Now, a little practical, just for fun, a little practical extra here. My colleagues, as I'm drawing over here on the board, if we look at frequency, and this is the transfer function, it turns out that the filter, some of you probably remember this, at the cutoff frequency, the filter is already down 3 dB, 0.707. So in the quote-unquote real world, what you would typically do is either pick a higher order filter, so it drops off steeper, or make the cutoff a little higher. See, if you made the cutoff a little higher, it would stay flatter a little longer, then start dropping. So there's a trade-off here between the order of the filter and how higher you want to select the cutoff. So I was thinking that what happens if someone discussed this, I wanted to make sure they didn't lose points. So I said, we want to be at least greater than or equal to this. And you want to be less than this, but not too close to that either. You see? So I said, please give full credit if you have an answer in this range. But my colleagues, for our purposes, based upon what we've discussed so far, we want to be close to that frequency we want to get through. But just for the fun of it, you actually want to be a little higher. Okay? So you avoid that little cutoff. Now, what's the minimum sampling frequency of the A to D converter? Okay, here's the answer. It's pretty much 2 times the corner. So whatever you pick the corner frequency to be, it's pretty much that. But that's assuming, Wesley, a very high order filter. Very, very sharp. If you go back to this filter here, you still got a significant amount of energy above the corner. So actually, in reality, you'd want your sampling frequency to be higher than the corner, because it's not a perfect filter. I'm still getting energy at these higher frequencies. So I tried to capture this in the answer key. 2 times the answer to part B. So the sampling frequency is 2 times the highest frequency. That's the Nyquist sampling rate. And it comes down to how do you define the highest frequency rate. And I chose it to be the corner frequency, right? 637.5. So that's it. That's the whole story. How do we do? We're doing okay? All right. On to problem 7. There's 9 problems. 7, 8, 9, we're done. We're coming down the home stretch. Okay. I'll give you a moment to read it, then we'll go through it. You have an N-bit A to D converter. And we're using it, of course, to digitize an analog signal. Now, be careful of the second sentence. The sampling rate is 1.5 times the minimum required. This is very realistic. We often oversample. See, if you just do the minimum and you miss a sample, you're going to miss something. So the minimum sampling rate is 2 times the highest frequency. We're going to sample at 1.5 times that. So it's 1.5 times 2 times the highest frequency. And determine the number of bits generated to digitize a signal of t seconds duration. So there's no numbers really. There's the 1.5. And the highest frequency is f sub h. So the minimum required sampling rate 2 times f sub h. But that's not the actual sampling rate. The actual sampling rate is 1.5 times that. So the total number of samples per second is 1.5 times 2 times f sub h. Now, we have an n-bit A to D converter. What does that mean? For every sample, the converter puts out n bits. That's what an n-bit converter means, A to D converter means. So we say, good. I have n bits per sample, and I have that number of samples per second. I think we got it. Okay. So if you just follow the units, a problem like this works so nicely with units, my colleagues. We got 1.5 times 2 times f sub h, samples per second, times n, bits per sample. That gives me bits per second. Perfect. And I'm asked to find out how many bits are used to represent a audio, a song or audio or something, an audio recording of capital T seconds. Well, T is in seconds. So multiply what we got, bits per second, times T seconds. I'm going to get bits, and that's it. We're done. How do we do? Now, help me out. How many bits in a byte? 8. Good. Good. Just in case. 8 bits in a byte. All right. We good on this? We're We're good. We're good. We're good. All right. Look at this. Ah. Shades of exam 1. Okay. Which is determining n. All right. So this is problem 8. This and the next problem, and we've done it. Problem 8. Filter design. You have a low-pass nth order filter. The sensor is connected to it. Now here's the deal. The highest output frequency of the sensor is 2,000 hertz. There's noise signal. The bad signal is at 12,000 hertz. So I said to myself, I got this. The noise is 12,000 hertz. The good signal goes up to 2,000. What I want is a low-pass filter. Let the low frequencies through and knock out as much of the noise as I possibly can. Now, again, going back to our discussion on the A to D, filtering issue we had just a few moments ago, in the real world, we probably wouldn't pick the corner frequency of the filter to be exactly the frequency that's the highest frequency at the output, because that's assuming a perfect filter. We would pick the corner a little higher, but just to keep life simple for us, we're going to make the corner frequency of the filter the highest frequency coming out of the sensor. So we're selecting the corner to be 2,000. Now, we are required to have the gain at the noise frequency. The noise is 12,000 hertz. We want that to be minus 45 dB. Now, I'm hoping you remember to use that crazy formula I give you on the formula sheet for G. G has got to be non-dB. All right? So I got to convert G to non-dB. So minus 45 is 20 log to the base 10 of G, and you're all set. Now, my colleagues, be careful. I had 1 or 2 colleagues come by my office to discuss exam 1. This is an easy place to make a mathematical error with your calculator. You got time. You got 4 hours for this exam. Double check. Make sure you got this. So now the gain in non-dB is here. I'm hoping the rest brings back fond memories. I now go to the gain formula for the filter that we're working with. And the only thing to be careful of here, after you get it into non-dB, is be careful not to mix up F and F sub C. F is the frequency that I want the gain to be measured at. So we want the gain at 12,000 hertz to be minus 45. So F is 12,000. The corner frequency is what we picked based upon the highest frequency out of the sensor. My colleagues, the rest is here. I'm sure you're well able to carry this out. You can look this over. Last item, even if N was 2.01, becomes 3. Because if you were to go and put 2, if you found out N was supposed to be 2.1, and you went back and put in 2 to this equation, your gain wouldn't be wouldn't meet the requirement. Okay? So you always go up. It's not a rounding. You always go up, even if it's 2.1. And N has to be an integer. So my choices are 2 or 3. Forget 2. This is 2 point something. That's enough to tell me it's 3. All right. Good on that? I think this is a useful skill to have, filter design. All right. All right. Is there a part B to this? No. We're coming down the end. We finish with a classic. Eamon, suppose you're walking along Washington Street in June, and someone comes up to you and says, "What is loading error?" How would you describe it to them, and, without using equations? How would you describe the loading error of a circuit? Right. Person just came out of McDonald's, is happy, and sees you and says, "You look like a person out of Stevens. I've often wondered, what's the loading error?" How would you describe it to him? Yes, you can. And William can call on me. Okay, I think the easiest thing to say to this person is the before minus the after. Okay, I have a circuit. At a particular point, I measure the voltage. Good, that's the before. Now, what do? I add a load. For our purposes, a load is a resistor. And I think of Mechie, right? I got a beam, I add a load, what happens to the beam? Goes down, right? Bends a little bit, right? Tiny amount. That's what happens in a circuit. The voltage before now changes. How does it change? Gets a little bit less, depending upon the resistor that you add. So Eamon and Will, what I would say is before minus after and keep walking. Okay? So it's before minus after. So I say excellent. So we read here, we have an attenuator. My colleagues, this is an attenuator. It's going to lower the voltage. Here is the Thevenin equivalent for a sensor. So we have the Thevenin equivalent for the sensor. And we take the output across R2. I give you all the numbers. Determine the loading error due to RL. So my colleagues, just to wrap up, I'm going to measure this voltage without the load. Then I add the load, and I measure the voltage. The second reading will be lower than the first if you've done it right. Take the difference. That's the loading error. And I give you all the numbers. A wonderful tool to use is voltage division. So let's get the before. The before says, I'm taking the voltage across to 25K. I'm sure you remember voltage division. You put that resistor in the numerator. And all the other resistors are in series, so I divide it by the sum of all those resistors. So all three are then in the denominator, multiplied by the Thevenin voltage, which is 15 millivolts. So with no load at all, it's 10.66. Now, if I do this right, my next calculation is going to be lower. Okay. So what do we now do? We now add a load resistor. The load resistor is 40 kiloohms. My colleagues, I hope you remember that, excuse me, I cannot directly use voltage division now. I have resistors in parallel. So we find an REQ. Exactly. We find an REQ, and we're done. I think that's it. Excuse me. We now add a load resistor of 40 kiloohms. It's going to lower the voltage. So the first thing I do, excuse me, let me just get a quick drink of water, is I calculate REQ. Okay. I calculate REQ, and now I don't see two resistors here. I see one. Now I can do voltage division by putting REQ in the numerator, and now be careful, divide by REQ plus the other two resistors. Multiplied by the input, which is 15 millivolts, and notice we get a little bit less than before, 9.028 millivolts. And as Eamon and Will told me, the loading error, I spelled before without an E. I never noticed that before. See what happens when you get a PhD? You start to not spelling things right, and it takes you years to notice. So it's before minus after, and we get an answer. That's it. We're done. Now let me see, were there any other problems? Extra credit questions. And that's it. I think we're done. Thank you. Applause goes to you for being here. And applause go to Tariq from SITTV and all his colleagues. Excellent. Thank you. You're making a big difference because this class has about 300 colleagues. We don't have 300 people here tonight, so you're making a tremendous difference. Thank you. Anything else before we wrap it up?